This is section 2.3, continuity. We're going to define continuity in regards to different parts of a function's domain. A function could be continuous over part of its domain or all of its domain. So first we're going to define that, let's say that this is a number line. We're going to have a be the left endpoint of a function, b is going to be the right endpoint of the function, and c is going to be some interior point. So we're going to start off with talking about continuity at a left endpoint, x equals a. A function is going to be continuous at a left endpoint so long as the limit as x approaches a from the right. So this is a left endpoint. You can only approach the function from the right, or the number from the right, of the function. And that has to equal f of a. Okay, so we're saying that the limit exists as you approach it from the right, and we're also going to say that the function itself exists. Now I'm actually going to skip the interior point at x equals c for just a second and talk about the right endpoint. And this is at x equals b, and as you can imagine, the limit as x approaches b. Now if this is the right endpoint, we can only be approaching this thing from the left. And don't forget your argument, the function. And in order for a function to be continuous at a right endpoint, the limit has to exist and the function value has to be the same. And when we talk about an interior point at x equals c, the limit as x approaches c of the function has to be the same as the function value itself. Okay, so those are the definitions for continuity at a left endpoint, an interior endpoint, and a right endpoint. Now, as I've said, a function can be continuous on part of its domain and discontinuous on another part of its domain. As you look at this graph right here, there's a kind of like a piecewise function going on with some parts that has a hole, there's a jump. So we're going to talk about just using your intuition and using what you think about this graph. Take a look and try and figure out where the function would be considered continuous based off of what we said above, and where it would be discontinuous. I'm going to have you pause it and write down your thoughts and then come on back. Okay, so how'd you do? Let's see. Continuous. As I look at this graph, let's first check the left endpoint. At x equals 1, in order for it to be continuous here, the limit would have to equal the function value. And I already see that there's kind of a hole with a separate point at x equals 1. So this is going to be discontinuous at x equals 1. As we move along, though, from x equals 1 just to the right of it, all the way until you get to this point right here, x equals 4, this entire region is continuous. There are no jumps, the limit always exists there. So we're going to use interval notation, and I don't know how familiar you guys are with interval notation. If you don't include a point, you use parentheses. If you want to include the point, you use a bracket. So, but we're not going to use the point at x equals 1 because it is not continuous there. There's a jump. And this is going to go all the way until the coordinate point x equals 4. We do not want to use x equals 4 because that's where the jump is. So then the entire region is going to be continuous. If we look at the location from 4 all the way until 6, that is also continuous. There are no jumps, no holes, anything like that. So we are going to say from 4, not including 4, all the way until 6. And at 6, we actually are going to include that endpoint, because at the endpoint, the limit, the function has to have that limit from the left, and it does. The limit would be 4, and the function value at 6 is also 4. So because of that, at x equals 6, you do have a continuous function. So the only other location where this thing is discontinuous is at x equals 4. Okay, so how'd you do? Let's go ahead and go to the next page. There are 4 types of discontinuities that we are going to be talking about, 3 in depth, and 1 of them I'm just going to mention. The first type is removable discontinuity, and this is what happens when you have a rational function and you are able to factor out the piece and cancel it that makes a 0 in the denominator. So let's kind of walk through the notation here. For a removable discontinuity, you're going to have the limit as x approaches c from the right of f of x equal the limit as x approaches c from the left. However, the limit is not going to be the same as the function value. So this is the first type of removable we're going to talk about. So it could look something as simple as perhaps this. And that's supposed to be the same continuous, the same y value on both sides of that guy. And then you would have to have a coordinate point somewhere else. Okay, so at this location, the limit from the left equals the limit from the right, but the actual function value itself is a different value. So this would be considered a removable discontinuity. You guys studied those in pre-calc last year. Additionally, you could have a removable discontinuity where the limit exists from the left, the limit exists from the right, and those two things equal each other. However, the function value is non-existent at that location. So we'll just pick this point here and we'll call this C, and we could have something as simple as this. Okay, with no coordinate point at x equals c this time. So the function doesn't exist there, but the limit does. And that obviously is a discontinuity as well. The next type of discontinuity is called a jump discontinuity. For a jump discontinuity, it's exactly what it sounds like. There is a jump in the graph, and this could be formed by a piecewise function. And we'll call this guy C. The limit from the left does not match the limit from the right. It could be filled in at x equals c. It could be open circle, but it can't be filled in for both of the piecewise functions. So this is considered a jump, where as you're approaching that x value of c, all of a sudden you get to c and there's a jump. Okay? Next page. For an infinite discontinuity, it is exactly what it sounds like. We are going to have a vertical asymptote here, and we're going to have a function that approaches that asymptote, and it cannot be continuous because at the location of x equals c, the function does not exist there. So actually I forgot to write that over here. This would be the limit as x approaches c of f of x does not equal f of c, and additionally you would have to say f of c does not exist. Okay, so perhaps this thing does have a limit, maybe from the left and from the right, both sides are going towards infinity. Perhaps it doesn't have a limit, but either way there's a discontinuity happening because of a vertical asymptote. And for the final discontinuity that we're going to talk about, this one's called oscillating. It's not something I'm going to spend a lot of time with, and I'm going to have you do something on your own right now. I'm going to have you graph this guy into your calculator, and you're going to see what happens as you zoom in closer and closer to x equals 0. And I'm going to show you a brief graph of it, but anything I draw is not going to look anything like it. I do a little squiggle, and you'll see why. If you graph this, and then you continue to zoom in towards x equals 0, what's happening is you're approaching, in this case, the limit as x approaches 0 of this sine of 1 over x. What's happening is you approach 0 from the right. You're taking 1 and you're dividing it by very, very, very small positive numbers, which is going towards a very large number. When you take the sign of a very large number that continues to get larger, your sign values are fluctuating back and forth and back and forth and back and forth, and it happens so quickly that it's called oscillating. We can talk more about this in class tomorrow, but if you, again, graph this function and you zoom in continually over and over towards x equals 0, you'll see what I'm talking about. The graph kind of goes berserk. But again, we're not going to spend much more than this on it, okay? Continuity itself has a pretty intuitive approach to it. If you can draw a function without lifting your pencil off of the piece of paper, that's pretty much a continuous function. Okay? For part 2 of continuity, a function can be continuous on one part of its domain and discontinuous on another. Okay, that's what we encountered in that other example on the previous page. Example 1, I believe. So there were parts of the function that were continuous, they were smooth, you didn't lift your pencil to draw them, but then other parts there were jump discontinuities or removable discontinuities, etc. Okay. For part 3, the 3-part definition of continuity is just bringing all of this together. In order for a function to be continuous, you must have the following 3 things. The function must itself exist at the location in question. The limit, as x approaches that number in question, must also exist. And I suppose I should say exists. And then the last part, which ties everything together, and this was that intuitive piece. The limit as x approaches c of f of x must equal f of c. If those 3 things don't happen, you do not have a continuous function. I would like for you to pause this presentation right now and try to draw the situations on this page. And I'm really not sure. I tried 3 times to delete this thing. Microsoft Word was giving me a pain in the butt trying to do this. I don't know why that's written there. It's not supposed to be. The graph is supposed to be clear. But please try right now, press pause, and draw a function that is continuous that has a limit at x equals 1, a function that is not continuous but has a limit at x equals 1, and then a function that is not continuous and also has no limit at x equals 1. And let's see how you did. All right, let's see what you came up with. And your answers might be different than mine. If you come up with a drawing that's different than mine, please show me in class tomorrow or make sure that you bring it up to the class and we'll see if we all agree with it. So for part A, a function that is continuous that has a limit at x equals 1. This can be anything. It can be a nice smooth function. It could have been a line, as long as it's not a vertical line. As long as it is smooth, you never pick up your pencil at x equals 1. That's all we're looking for that one. For part B, a function that is not continuous but does have a limit at x equals 1. This could have been a removable discontinuity. Something maybe that looks like that at x equals 1. And then for part C, a function that is not continuous and has no limit at x equals 1. This could have been anything from a vertical asymptote to other things, which I don't want to give all the answers away, but this was what I decided to do. And let's not even have it have a limit at all. So in order for it not to have a limit, I'm going to have the function approaching different infinity values. From the left of x equals 1 is going towards positive infinity. From the right of x equals 1, this is going towards negative infinity. Okay. So that is some example graphs. And again, if you had something different, make sure you show me in class tomorrow. Example number 4 is asking you to find or to determine whether or not the functions are continuous based off of the definition of continuity. So remember that 3-part definition. The first thing that has to happen is the function must exist at the point in question. I don't know why I'm having such a hard time talking right now. Let's take a look. We've got for A and for part B, we are looking at a piecewise function, and the function themselves, each piece, would be continuous. 5x plus 3 and x cubed plus 5, both perfectly fine, no possibility of any asymptotes or jumps in anything on either of those pieces. So the question is the function continuous at x equals -1, where the split happens? Okay, so let's go ahead and take a look. I don't know why that's moving around. Let's go ahead and take a look at the 3-part definition. The first thing that has to happen in the 3-part definition, f of -1 has to exist. So in order to determine what f of -1 is, you just have to look at the proper piece of the piecewise function. We want to know when x equals -1, what is the function value? If you look at the domains that are defined, we're going to be following this bottom function because that is the function that's defined at that location of x equals -1. That being said, we'll plug in a -1. And that's going to give us a value of 4. So the function does exist and the function value is 4. The next thing you have to do is see if the limit exists. In order for the limit to exist, the limit from the left has to match the limit from the right. So let's check it from the left first. Remember I had said if you are checking a one-sided limit, you have to just determine which function you're going to be using if you're talking about a piecewise function. So the limit from the left means that we are going to be evaluating this guy. As x approaches -1, we can drop the from the left because we're going to be using the top function. If I can substitute now. X is approaching -1. -1 times 5 is -5 plus 3 is 2. So the limit from the left is 2. The limit from the right, we've actually already done, believe it or not. From the right, we're going to be using the bottom function, but we've already substituted and plugged that in, and we've already found that that is 4. So here's where you see that the limit does not exist. So this is not continuous. Okay, it does not have a limit, therefore that function is not continuous. I would like you to press pause and please try the second one on your own and then come on back. Alright, so how'd you do? I just put my work up. One thing I want to draw your attention to is, did you call it h of x? In your notation, did you make sure that you used the function h because that's what was supplied to us? If you didn't, highlight it, circle it, do something that draws your attention to it. These are easy points to lose on an AP exam. You don't want to do that. If they supply you with a function named h or named g, you want to make sure that you're using the same function name. Okay, so let me just talk you through what I did. The first thing was just to make sure that the function existed. So h of 1, you'll see the two domains here. 1 for x is less than 1, 1 for when x is greater than or equal to 1. So I used the bottom function of the piecewise. I plugged in x equals 1. I get out a y value of -5. So there is a function value there. The next thing that you have to check is, does the limit exist? Again, because this is a piecewise and it breaks at x equals -1, I'm going to check this function as x approaches -1 from the left, and then I'm going to check it as x approaches 1 from the right. If you are approaching from the left, you will be using the top function. So I plugged in that 1. Watch your order of operations here. 1 is being squared and then a negative is being applied to it. So it's -1 minus 4, so you get the -5 out. As limit as x approaches 1 from the right of the function, so we already actually did this one. We just plug in the 1 and we're getting out a -5. The left and the right hand sides match, therefore the overall limit does exist, and because the function value and the limit match, this is a continuous function. In this example, we're given a piecewise function that is defined as a linear function for x less than 2, and it's defined as a quadratic for x greater than or equal to 2. K is a constant in this one, and for part A, they are defining that k equals 1. So the first thing we're going to do is we're going to sketch the graph at the right, and my sketch is going to be very crude, and I apologize for that. But I'm going to start off with drawing the x plus 1 function, and if any of you had any difficulty with drawing piecewise before, I'm going to show you my technique that I use. The first thing, x plus 1 is in slope-intercept form, so it's going to go through y equals 1 when x equals 0, and it's going to have a slope of 1. So I'm going to do my very best to draw a line that does that. All right, that's not too horrible. But this function says that that is only allowed, that's the only function, the function is only defined when x is less than 2. Not for x even equal to 2, only when x is less than 2. So at x equals 2, we would have had a y value of 3. Right? You plug it in, 2 plus 1, you get a 3 out. So at 2 comma 3, there's actually going to be a little hole. Okay, so that's at 2 comma 3. The rest of the function for x greater than 2 does not exist. Okay, I'm going to try to draw that hole a little bit better too. Well, that didn't work at all. You guys might just have to use your imagination on this one. At 2 comma 3, there is a circle. Open circle. Okay? And I'm going to change colors here and use a... Oh, I can't use blue. That's Bear colors. Oh, let's use green. Sorry, guys. I'm a Packers fan. Die hard. Here we go. We're going to use green for this one. And this is a parabola. It has been shifted to the right by 5, so that's the vertex is going to be 5 comma 0. 1, 2, 3, 4, 5 comma 0. And for this part, they're telling us that k equals 1. So this is 1 times x minus 5 quantity squared. That's what our y value is. Now, regardless of how you learn to graph parabolas, some people learned the quick technique. Some people just plugged and chugged points, and that is fine. But I'm going to go ahead and sketch this graph in. Okay, I just drew it in. I had to pause it. It's so much fun to try and draw on this thing. But anyways, at the point in question at x equals 2, if you plug 2 in to the function here, 1 times the 2 minus 5 quantity squared, okay, y of 2 or f of 2, however you want to do this, you're going to get a y value out of 9. So the point 2 comma 9, that's what this should be getting up towards. 2 comma 9 is actually the point where the graph is going to start, and it's going to be valid for everything to the right of it. My pen is on the wrong color. Let's try this again. So at 2 comma 9, closed circle, going down, following the parabola, and the parabola goes on forever. Okay, it's closed circle because x is greater than or equal to 2. So this is what the graph looks like, and determine whether the graph is continuous at x equals 2. Go ahead and write your answer down, and you should say no. It's not at all. There is a jump, discontinuity. You had to definitely lift your pencil in order to draw this thing. Now for part C, it is asking you to find a value of k that would make this graph continuous. We plotted a function when k equals 1, and it certainly wasn't continuous. So I ask you now, think about what would have to happen to the graph in order for it to be continuous. What would have to happen to the y values for each part of the piecewise? Hopefully you're thinking that the y values for each part would be the same. Now we already know for the left-hand side we're getting out a y value of 3. Ideally, if we could get that out for the right-hand side, for the bottom part of the piecewise function, that would make it work. So how do we go about doing that? Well, here's what you do. You want to make the function continuous at x equals 2. This is the x value where we want it to happen. So at x equals 2, we want the y values to match. Okay, the y values from the left, and let me go back up and look here, the y value from the left, everything was x plus 1. We want that to equal k times x minus 5 quantity squared. Okay, we want these y values to match at x equals 2. So what I'm going to do is I'm going to plug the 2 in for x because that's the location where I need these y values to match up. And if you simplify this, 3 equals k. 2 minus 5 is negative 3. Negative 3 squared is going to be 9. So 3/9, which ends up being 1/3. So for this function to be continuous, for those y values to match up, you would have to have a k value of 1/3. So the left hand piecewise still looks like that, and the right side piecewise, the 1/3, remember, kind of, sorry, that's supposed to go through 5, 0. The 1/3 is going to make this graph a little bit wider, and it actually fills in that location because at x equals 2 now, we're getting out 1/3 times 9. So we're getting out that y value of 3. Okay, and that concludes this lesson. So if you have any questions, make sure you guys ask me tomorrow. I'll see you then. Bye-bye.